It's one of life's greatest achievements and one of its most enduring mysteries. It divided generations of scientists and launched one of the hottest debates in history. How and when did birds learn to fly? Birds may be the most versatile creatures that ever lived. They can move at speeds of up to 175 miles an hour. They can soar 30,000 feet into the stratosphere and dive 30 feet into the sea. Some migrate 20,000 miles in a single journey. Some can glide effortlessly for days, while others flap their wings over 50 times a second. They come in an infinite variety of shapes and sizes and are found on every continent and in every habitat on Earth. From high overhead, they have witnessed events no other creature has ever seen: the coming and going of the ice ages, the drift of the continents, and the end of the 180 million year reign of the dinosaurs. But the most amazing thing is their ability to fly at all. How these remarkable creatures took to the air has confounded scientists for centuries. In 1859, Charles Darwin proposed that all living things come from vastly different creatures modified through natural selection. To help him persuade skeptics, what was needed was a link, an animal trapped somewhere between the past and the present. 2 years later, workers digging in a German quarry uncovered the remains of a prehistoric creature with wings. On the wings were the distinct impressions of feathers. Called archaeopteryx, it bore a striking resemblance to a modern bird, but its other features were puzzling. It had a long bony tail, 3 sharp claws on the edge of each wing, and a prominent jaw with sharp teeth. Here was the missing link, but where did it fit in? 150 million years ago, during the Jurassic period, the world as we know it did not exist. Dinosaurs ruled the Earth, and shallow inland seas covered much of the continents. The landscape was of conifers and ferns, and flowers had yet to appear. The skies belonged to insects like giant dragonflies and flying reptiles called pterosaurs. Below was Archaeopteryx. With outstretched wings, it would have been able to make short gliding flights, but no more. Still, the origin of birds lay unresolved until the discovery of a dinosaur with features reminiscent of Archaeopteryx, the bones in its claws, its long tail, and the shape of its skull. Called Velociraptor, it was quick, agile, and ruthless. One lunge, and it could snatch its prey and tear it apart. Although Velociraptor lived over 80 million years ago, the architecture of its arm resembles the wing of a modern bird. Its discovery revived a 60-year-old idea that Archaeopteryx evolved from a small, 2-legged dinosaur. But what happened next in the bird story remained a mystery. Louis Cheape of the Museum of Natural History in New York has spent his academic life trying to fill in the missing pieces.
We knew that Archaeopteryx, a bird that lived 150 million years ago, had feathers and wings and was able to perform some sort of flight. But we didn't know what happened in between Archaeopteryx and birds of basically modern design.
Archaeopteryx remains the oldest bird ever found, but the next 65 million years of evolution constitutes a huge gap in the fossil record of birds. A bird is masterfully engineered to fly. Its bones are hollow and light, and not easily preserved. The rarity of bird fossils left a big question unanswered. How did the first gliding birds like Archaeopteryx take to the air? Then, out of the blue, came a landmark discovery in Spain. To fill in the missing link in the fossil record, Louis Cheape has been summoned to the other side of the Atlantic by an old friend, Professor José Sanz of Spain's University Autónoma in Madrid.
Bien, ningún problema. Todo perfecto. ¿Cómo andan las cosas por acá? Nada, aquí trabajando un poquito.
This limestone outcrop, called Los Hoyos, was discovered in the 1980s by an amateur paleontologist. Since then, it's become one of the most productive digs in the world.
Así que estas son las cuadrículas.
Las cuadrículas, cada una tiene un...
Over 90% of these rocks have yielded fossils, allowing scientists a rare glimpse of what Los Hoyos was like in the distant past. A 100 million years ago, during the Cretaceous, a murky lake fringed with reeds and marshes teemed with life. Primitive crocodiles, turtles, fish, and shrimp filled the water, while clouds of insects swarmed overhead. In the background loomed a tropical forest that sheltered dinosaurs, lizards, salamanders, and frogs. Above, the sky was filled with birds. A few, when they died, fell into the lake and sank to the bottom, where they were covered over by sediment. A lack of oxygen in the mud meant a lack of scavengers, ideal conditions for preserving not only bones, but soft tissue and feathers. Every fin and bone, even the scales and cartilage of this prehistoric fish, are etched in exquisite detail. Despite the wealth of fossils from Los Hoyos, the rarest of all, an early bird, remained elusive. But in 1985, the first of three, dating back 115 million years, was uncovered.
The fact that we have found only 3 birds from here does not imply that birds were rare then. They were probably as common as they are today, but simply that they are less likely to be preserved as fossils.
The first, called Iberomessornis, was the size of a sparrow. Its legs and pelvis were still shaped like a dinosaur's, but its toes were clearly designed for perching on the limb of a tree. Astonishingly, 6 years later, a second appeared. Concornis was a bird the size of a robin, but its feet and claws still belonged to a dinosaur. Then, in 1995, came the third, so well preserved that its last meal, a tiny shrimp, can still be seen in its stomach. Eoalulavis was also small and probably lived near the water's edge. Together, the three Spanish fossils were dramatic proof birds had come a long way since Archaeopteryx. Like these modern finches, their bodies were smaller, streamlined, and more compact. Their skeletons were lighter to reduce weight, and their wings were more fully developed. Although they retained some features of the dinosaurs, they could do something Archaeopteryx could not. Each had found the secret of powered flight. When mankind first tried to emulate the birds, flying looked easy enough. But flapping a pair of crude makeshift wings didn't seem to work. Though daring, inventive, and often absurd, no matter how hard we tried, we never seemed to get off the ground. The principles of flight eluded a host of would-be aviators. As antique plane expert Jeff Green well knows, he's long been interested in the history of how man turned to the birds to learn how to fly.
We had a famous King of England who tried to do just that and strapped a mechanism to himself and jumped off a tower. And he became, as far as we know, the first recorded statistic of a fatal injury attributed to structural failure. Mind you, they did blame that on the fact he used chicken's feathers instead of eagle's feathers because a chicken couldn't fly anyway.
By the end of the 19th century, the dream of flight turned to the study of the properties of air and the aerodynamics of wings. Orville and Wilbur Wright watched vultures gliding through the fluctuating air currents near their home in Ohio and realized that the secret lay in the shape of the wings. They needed to be lightweight but still strong and large enough to produce lift. They also needed an engine to give them momentum and forward motion. In a bird, the power to fly is supplied by its wings. Flying appears graceful and effortless, but a wing may be the most sophisticated of all natural creations. By a complex combination of vertical and horizontal movements, wings not only act like aerofoils to produce lift, but also act like propellers, pulling a bird through the air. To flap a wing requires an impressive set of muscles, but according to Jeremy Rayner of Bristol University, without one particular muscle called a supracoracoideus, a bird would run out of energy.
But what's special about it is it attaches to the wing on the upper surface of the wing. It attaches up here. That means that when it contracts, it pulls the wing up. It's effectively attaching here, and it yanks the wing into the upstroke.
This muscle allows a bird to save its strength by executing the upstroke with little or no effort.
Now, Archaeopteryx and the early, very first birds didn't have that. That means they didn't need to use the wing in the upstroke. It tells us from what we know of the aerodynamics that they couldn't fly slowly.
Compared to Archaeopteryx, the Spanish birds boasted other new features. There was a large breastbone for the flight muscles, a strengthened pelvis to take the weight of landing, and a shortened tail to act like a rudder. Still, the Spanish flyers had yet to rival the efficiency of modern birds. Flight burns an enormous amount of energy. The average bird beats its wings hundreds of times a minute. Because energy consumption is accelerated, their blood pressure is higher than any other animal, and their hearts are larger. To meet the demands of flight, the anatomy of the Spanish birds was modified. Body functions such as breathing and blood circulation became more efficient, but most dramatic was the change in size. It was no coincidence they were all smaller than a robin.
Most of the variation in birds as they learnt to fly happened when they were much smaller. And that helps because being smaller, you're more flexible in what you can do. These constraints of energy and design aren't nearly so strict.
Although birds today display myriad varieties, the differences are superficial. The length of their legs, the shape of their beaks, and the color and designs of their feathers are all adaptations to lifestyles, not flying. Underneath lies a remarkable uniformity.
There's really only one way you can build a flying bird. If the wing was too big or too small, the animal simply wouldn't be able to fly. And that's also the reason why birds are relatively small. Even the largest flying bird weighs little more than a domestic cat.
The perfect ratio of wing size to body weight may keep a bird in the air, but it took the evolution of one tiny bone to bring it down. The discovery of the first two fossils at Las Ollas revealed that the Spanish birds had most of the characteristics of modern flyers, such as shorter tails for maneuverability and well-developed breastbones to anchor their flight muscles. But the discovery of the third bird, Io alulavis, added an ingenious new feature to their design. On the bones of its perfectly preserved wings was a tiny appendage, which corresponds to a small tuft of feathers. Though less than a half-inch long, it was nature's solution to a fundamental problem. What goes up must come down. Like an airplane, a bird can't land without first slowing down, otherwise it will crash. To reduce its speed, a bird deploys the feathers on a small bone on the leading edge of its wings, called an alula, or bastard wing. The bone has its origin in the dinosaurs. When the forelimb was evolving into a wing, the equivalent of its thumb grew feathers, creating the alula. When the angle of the wing is increased in flight, the airflow over it is disrupted, causing a bird or an aircraft to stall. An alula allows the wing angle to increase without disturbing the airflow, allowing a bird to slow down. Just after World War I, aeronautical engineer Handley Page watched birds land and adapted the principle of the alula in his airplane designs.
Basically, this was Handley Page's invention to give the aircraft greater maneuverability, particularly at low speed. And the idea of this was that the air flow coming to the wing would go under here and thus would stop the wing from stalling. It again was a rather crude method of trying to give the pilot more controls, which the bird has inherently available to it.
Thousands of times a day around the world, jets land safely, flaps down, thanks to the alula. As in modern aviation, this one simple concept began a new chapter in the story of the early birds and what they could do.
They were certainly able to do sophisticated flights and to maneuver, for example, between branches and to take off from a ground level and to do pretty much everything that we see doing in a modern bird today.
35 million years after Archaeopteryx, there was no turning back. Liberated from their earthbound origins, birds were free to explore the world, and explore it they did. Once only able to glide short distances, birds now became accomplished flyers that could travel thousands of miles and stay aloft for days. With new machinery to soar above the earth, propel themselves through the air, and land safely, all obstacles vanished. As the unchallenged owners of the sky, there was no competition. Over the horizon lay a new frontier. Birds were free to cross oceans and continents, to travel from pole to pole and sample new and exotic environments. Getting from place to place was faster, seeing where they were going was easier, and escaping from predators was quicker. During this time, the Earth was undergoing an extraordinary transformation. Continents were breaking up, ocean currents were shifting, and the climate changing. Out of this upheaval, new life forms appeared, among them the first flowering plants. Flowers with their pollen were an abundant new source of energy for insects and birds. They ushered in a whole new food chain and triggered an explosion of diversity. Modern birds come in every size, shape, and color. From the flightless to the most accomplished aerialists, they total over 9,000 species. But today's birds are no match for the variety of their bizarre relatives that inhabited the Cretaceous tens of millions of years ago. There were birds like the fast-running Alvarezsaurus with the tail of a dinosaur, the flightless Paleoworld with thick, sturdy hind legs and tiny, stunted wings. And there were others even weirder, like Neukinornis, with teeth and vicious claws for grasping prey, all living at the same time as the dinosaurs.
The way I think of the diversity of birds in the Cretaceous approaches what we see today in the mammal world. Then in the Cretaceous, we had birds that were probably as different as today are bats, whales, and humans.
If we could go back, we would see a land dominated by a variety of different dinosaurs. In the waters, enormous crocodiles, and in the air, pterosaurs. And completing our new picture of the time was another creature.
Now we know that we would also see the sky filled with a variety of many kinds of birds.
Each new day at Las Ollas is filled with promise. New fossils are constantly being uncovered, but the next bird has yet to be found. One important missing link has been filled in by the discoveries of the three birds, but still the hunt goes on to answer other burning questions on their evolution. Is Archaeopteryx the direct ancestor of the Spanish birds? And were the Spanish birds a direct ancestor to modern birds, or were they just an offshoot? In the meantime, the paleontologists can be satisfied that they have stumbled upon evidence of what may be the greatest turning point in bird evolution. They had learned to fly. Like no other creature on Earth, they soared into the sky. They exploited new opportunities, adapted to new environments, and diversified in infinite ways. In the twilight of the Cretaceous, the birds took one final dramatic leap into the future. 65 million years ago, a handful escaped the fate of the dinosaurs to become one of the most successful creatures that ever lived.